name is Jose Lubayo. I'm here with Andrew Mays and Hannah Holden. We're Team Raytheon, and we're going to be presenting our Capstone project, the Digital Reference Hydrophone. A hydrophone is an electronic device capable of receiving underwater acoustic signals and translated into voltages. What motivated this project is that hydrophones are used to test and measure transmitters. Our device will reduce the time required to debug problematic issues with the system. The proposed device will consolidate the current multi-channel test facility into a single-channel device capable of data acquisition and control functions. This will result in saving time and money to Raytheon.
In service of this goal, the best possible product we could make is one that follows all of the design outcomes specified by Raytheon, namely the ability to take analog voltage signals from a hydrophone, convert them into digital data, packetize them in the processor, and send it off to a PC for later analysis with more software that we are making. In addition, it needs to be simple, easy to use, and flexible. For example, we're making it self-testing because it will actually generate a test tone internally that you can use to debug the system in case there's any errors. It'll be configurable with various analog filters that you can set in software on the PC end to which one's being used. And it'll be configurable on the fly in between tests. As such, this is a heavily boiled down version of our design so far. Please note the real diagram takes up more than the entire wall, and we have like 10 pages. The hydrophone's analog voltage signal is sent through the analog filters off to the analog to digital converter, which converts into 24-bit integers, which go into the programmable logic, which converts to 32-bit floats, which are saved in block memory in the PS, which is read by the processor, put into packets, and sent over the Ethernet link to the PC. Regarding the ARM processor, the Ethernet link, and the PC, that is my domain of the project, which is software. So far, what I've gotten done is block diagrams, which basically are a roadmap for how all the functions of the product will interact with each other and will be laid out. More specifically also, we have state diagrams, which dictate exactly how the software, step by step, performs its functions. Example given here, again, simplified. Message maps, which dictate exactly how the FPGA and the PC will communicate with each other. And the first stage bootloader, which will be used to program the board with our software and hardware designs. And now for hardware, we'll say.
So for the hardware section of the project, I started designing the block diagram and defining the function characteristic, such as the total gain needed and the gain I needed per stage. After I finalized defining the function characteristics, I was able to start designing the filters. I started by designing the low-pass filters in stage 2. In stage 2, we'll also offer an amplifier circuit with no filter. When I was done designing the amplifier circuit, I moved back into stage 1 and designed 4 bandpass filters for each individual hydrophone. These are active bandpass filters, which mean it adds additional gain into the signal. The reason that we want to add additional gain into the signal is to maximize the input range of the ADC, which connects to the FPGA.
For the firmware side of our project, we have recently finished all of the planning stages. This includes block diagrams, defining our parameters, a register map, a programmable system, and a Berg stack pinout. The block diagram was vital for us to understand all the capabilities of our FPGA. I then defined all of the parameters that the user will have control over. I took those parameters and put them into a spreadsheet known as the register map. The register map defines the length, location, and how the FPGA interprets all of the bits. From there, I created a project within Vivado. This is the programmable system, as shown here. The programmable system has our Zinc chip, which controls the master clock, reset, GPIOs, DDR, and fixed IOs. The other key feature is our 3 dual-port VRAMs. We have 3 dual-port VRAMs, each servicing a different portion of our project. The reason we chose dual-port VRAMs was so that as the Zinc writes to the VRAMs, the ARM processor can simultaneously read. I then created a separate project within Vivado where I did Berg stack pinout. Here I took all the signals traveling from software to the PCB and placed them based on voltage and drive strength. After this was complete, I was able to export a constraints file for the FPGA, as well as a spreadsheet for the Berg stack pinout, which will aid Jose in his PCB design. For our remaining challenges on our software end, we need to create a script that facilitates communication between our PC and our FPGA. The PC needs to be able to send a configuration script, a configuration file, over the gigabit Ethernet cable to the FPGA for initialization and setup. The FPGA also needs the ability to send packetized data samples back over the Ethernet switch to the PC, where we need to create a separate script in MATLAB which will read in this data and display it for the user. For the remaining challenges on our hardware and firmware side, we need to create VHDL modules that correspond to all of our block diagrams. We then need to create test benches and simulate them within Vivado. This will verify their functionality. For the PCB, we need to do schematic capture, board layout, fabrication, and assembly. Once all of this is complete, we will load the software onto the FPGA, connect our FPGA to the PCB, and move to an acoustic test facility where we will test our device until it meets the best anticipated outcome. Here's a diagram of our proposed test setup. And finally, we would like to thank all of those who have supported us.